for number 34, for chapter 34, 32, and 41. So let's see what we got here. All right, guys. Here they're talking about Maxwell's equations and electromagnetic waves and how this plays out. So, again, I got asked to read this stuff. I tried to go through what I could up to this point, and we got hit with what we got hit. So let me try to write a few things that are of interest vis-a-vis this stuff. I'll try to write a few things here. Let me just try to, I'll see where they kind of emphasize stuff, and I'll see what I can say about it. Say a few things, we'll kind of take it from there, I guess you could say. This is stuff you've already, believe it or not, in a backhanded way, they already kind of hit you with it. If you integrate over a closed path, if you integrate over a closed path of E vector, or over a closed surface for that matter, if you do an interval over a closed path of E vector dot dl vector, if you integrate over a path and want to find out what has happened, E vector dot dl vector is delta V. Delta V is the electromotive force. If there's not a lot of turns in the wire, just one turn in the wire, rather than negative n d phi b dt, it's just, rather than negative n d phi b dt, if there's n turns, just one turn is negative d phi b dt, or there might be a lot of turns, and they're just including the a lot of turns in the flux. It's already included in this phi. So that theoretically could happen as well. If you integrate, and this can be kind of, you gotta kind of watch it. I mean, we're talking about this. For our purposes, don't sweat this circular path thing. The big takeaway here is, are you integrating? Are you integrating E vector dot dl vector? That's going to give you a change in potential. The potential difference is the same as the electromotive force, and as we said last time, that's negative n d phi b dt. If the n is brought into the phi in one way or the other, then it's just negative d phi b dt to get that. Regarding something like that, you guys. And the way that can get written is, leave the negative as is, and integrate B vector dot dA vector. Well, that's BA. That's a fancy way of saying BA, but you're taking into account that there's a lot of variation that can occur, therefore you got to do an integral. But B times A is the flux, and if you differentiate the flux, then you got, so forgive me here guys, then you got, for right there, then you can write it as negative d dt of that. So negative d dt of this integral, B vector dot dA vector, is negative d phi b dt. Phi b is the integral B vector dot dA vector. The induced electric field is non-conservative. So the electromotive force, which is the integral over the closed path, E vector dot dl vector, is not equal to 0. So it's a non-conservative force right here. What gets set up is a non-conservative force. You're not, in many instances when you do something like this, you're coming up with 0. You do this with gravitation, you do this with other forces, you are very frequently just coming, even with the electromotive force, even with the electrostatic force in some regards, but in this particular case, the way this all works out, that's non-conservative. So that's not going to be 0. That's what was worrying me to begin with, but it's fine. generally it's not going to be equal to 0 when you're talking about the something induced having happened regarding this. The induced electric field is non-conservative, so this is not equal to 0. Then they talk about some other stuff. They go into Gauss's law for electricity. We've gone into this. I don't think it's going to look completely foreign to you when we look at it. If you integrate and find the flux through a surface, remember that EA we talked about, the short way is EA, the strict way is this way. That's the electric flux. That is equal to Qn over epsilon naught. We've talked about that as well. So there's pretty big stuff here, guys. I mean, the way it happens here. This, kind of watch out for it, because so many times when you go around a closed path, all the time, if it's a conservative force field, if it's a conservative field and you go around a closed path, it is going to be equal to 0. This doesn't happen when it's an induced EMF. So this conclusion is fine, and that's non-zero. Other places, when it's a conservative field, that would be 0, but not this case. And same thing with this. And that's really the stuff we've done before. Remember the EA, E vector dot the A vector, the integral of E vector dot the A vector is Q in over epsilon naught. So you got that right there. Here we get what Gauss talked about regarding magnetism. And what we have here is phi B that means what goes in, what goes out comes back in. Here, what goes out stays out. You know, when you're talking about Gauss's law for, let's have a look here. Gauss's law for electricity, whatever field leaves because of the charges that are inside, whatever field leaves, it leaves. It's not coming back. Here, the field that goes out hooks around and comes back in. That's why you got this thing equal to 0, whereas this case, if it leaves, it's indicative of a lot of charge being there. If there's a lot of flux coming out, there's a lot of charge inside. Here, regardless of the kind of B field that's happening, what goes in comes back, comes out. What goes out comes back in. And this right here is stuff we did when we were solving the problem when something was on the rails. Believe it or not, it was showing up. Not as much on the rails, but some other stuff that we'd actually looked at. Came out pretty good. No, when we were dealing with the stuff that was on the rails, indeed, we'd actually looked at that. So they're looking at this. Got Faraday's law. Again, they already kind of, it's already kind of been said. There's a general form, general form of Faraday's law. They said it again. What I said over here, you can look at it again and say, okay, what's going on here? How's this all happening? Because this is induced, it's non-conservative, so we got Faraday's law. It's looking like this. It's the same business we just did. First thing we did in this discussion, you guys, to get to here. We did this, and we did negative Ampere Maxwell's law. Same kind of business, you guys. B vector dot dl vector B vector dot dl vector equals mu 0 I through mu 0 epsilon naught Law not d phi e dt. There's a lot here, and we've dealt with it. I mean, we've dealt with it in the past. We looked at some stuff here. I just want to give you kind of, at least write some of this stuff down there, so it's we're looking right at it, I guess, up front when we see some of this stuff that we're going to look at. Again, it's in the back of the book. They do a pretty good summary on it. I think the problems are going to be pretty straightforward when we do it. There's some other stuff here, guys, and I am passing over it a little bit. Some stuff I'm not going to pass over. Electromagnetic waves are transverse. If a wave propagates along the positive x direction, its electric and magnetic fields are given by the following. So electromagnetic waves are transverse. If a wave propagates along the positive x direction, its electric and magnetic fields are given by the following. So if this thing was propagating, I'm just trying to figure out exactly how I want to say this. This thing was going in the, that's the x direction. This is x, and this is y, and this is z, and they're perpendicular to each other. This is associated with I hat, this is associated with k hat, and this is associated with j hat. It's propagating this way, and that means one of them is in the y plane, and the other one's, they're going, if it's propagating this way, you guys, the two fields, the B field and the B field and the E field propagate perpendicular to one another. They are perpendicular to one another as they go in the x direction. So one guy's in the xy plane and the other guy's in the xz plane. So the guy that's in the xy plane is the E vector, for example. So are given by E vector is a function of location and time, and that's equal to E max sine, and this is the stuff we did with strings, with ropes, some time ago, guys, and we didn't really get a chance to go into it now, I guess you could say. That's the guy going in the XY plane, like right on this board. And there's another guy coming out in the XZ plane, and that's going to be the B field. And the B field, also a function of X, also a function of T. That's not the issue. And this is B max, and it's the same exact equation. Almost. I mean, just about. I mean, the same structure of it, at least. And it's looking something like that. Then they got this thing called, mathematically, the energy transferred by an electromagnetic wave per unit time is given by the magnitude of the pointing vector, S vector. So they got this thing called the pointing vector. It's the stuff where you need a lot of time to do it, guys, and it's something we don't have time to do. So let me just talk about it. 1 over mu 0 E vector cross B vector, and so on and so forth. There's more stuff in there. We'll cross all the bridges as we need to cross them, I guess you could say. So, looking at this, let's see what we can say. We're looking at it, and we could say, all right, well, let's look at 32. 32 is saying, okay, for chapter 34, that is, right? Right. An electromagnetic wave is traveling in the positive x direction with the electric field oscillating along the z direction. If the wavelength is 555 nanometers, E max is 0.05 volts per meter. That's the same as newtons per coulomb. and the wave is in a vacuum, write equations describing the electric and magnetic fields that make up the electromagnetic wave as functions of x and t. They kind of pulled a fast one on us here. They made the oscillation go a little different. It doesn't matter. I mean, as long as they're saying it's oscillating in the z direction, that means the B one will be oscillating where the way they propose this guy could be oscillating. So it is the way it would look. So this is fine. I mean, the way they told us is okay, but they kind of pulled it a little differently on us now. They said that the E field, and it doesn't matter who's who, as long as they're perpendicular to each other. This guy's going in the K direction. Of necessity, the other guy's going in the J direction. So that's one way you could write it. So let's see what we'd actually say on that. And so we wrote it like this. I wrote it a little differently in the notes, you guys, but we're going to keep it like that. And let me just see here really quickly. We know a bunch of things. We know that, kind of on the side here, guys, I guess you could say, V, the velocity of propagation of a wave, is lambda times f, which is equal to c if you're talking about electromagnetic waves. Yeah, you remember from a while back, omega is 2 pi f, and k is 2 pi over lambda. So V is equal to omega divided by k. If you took this, 2 pi f, and divide it by 2 pi over lambda, the 2 pi's cancel, the lambda pops up. Those, that speaks a lot to us. That speaks a lot to us. They told us that lambda was 555 nanometers. 555 nanometers is 555 times 10 to the negative 9 meters. They told us E max remember that, they told us that. We know the units are different. The amount of energy in a B field and the amount of energy in an E field are identical. So this what I'm about to do is going to look, wow, it looks like one's a lot bigger than the other. No, the units are a lot different. But they're actually the same amount of energy. Whenever an electromagnetic wave is oscillating, there's the same amount of energy in the E field as there is in the B field. On average, they both have the same amount of energy. They both split up the energy of the electromagnetic wave. So there's a lot happening here, guys. So let's keep letting it happen, I guess you could say. As a general idea, E is equal to c times b. C is the speed of light. E max is c times b. Well, E max is c times b max. So what are we talking about? Well, they're telling us E max, B max. What would B max be? B max right here would be E max divided by C. So you can write it a whole bunch of ways. You could write one in terms of the other. Let's write it in terms of E. Maybe it might be a little bit. Maybe that's more the convention. So B max equals E max divided by C. Right here. Okay, sounds good to me. We said this guy was J because it's oscillating, the B field's oscillating in, well, they didn't tell us that. They said that the E field was oscillating in the X direction. Of necessity, the other guy's got to be perpendicular to him. So we get this right here. That's about it, you guys. I think we're going to be in, I think, pretty decent shape. We got this in the back of our mind to get us through this whole process. We got to find out who's who. Well, tell you what. Let's find the frequency. They already gave us what lambda is. Frequency is C divided by lambda. It's 3 times 10 to the 8th meters per second divided by 555 times 10 to the negative 9. 555 times 10 to the negative 9 is 5.55 times 10 to the negative 7. You say it any way you want to say it. Let's just get the numbers done here, guys. When you get that answer for F, find omega. Omega is 2 pi F. Omega is 2 pi times whatever this song and dance is going to yield after we do it. Omega is 3.4 times 10 to the 15 radians per second. Okay, if that's omega, kind of running out of chalk sometimes, guys. I'm going to mix up the colors on you here. Sorry. Omega is that. Yeah, why not? I mean, we're on a hot streak, I guess you could say. What's K? K is 2 pi over lambda. 2 pi is 2 pi. Lambda is 555 times 10 to the negative 9. K is 1.13 times 10 to the 7. Times 10 to the 7th inverse meters. Okay, there's a lot here. I mean, notice it wasn't that bad of a move to make. I mean, we saw, I wrote this. You could argue, you know, how important it is to us, but we know a lot of stuff. We know that it's important enough that you remember omega is 2 pi f and K is 2 pi over lambda. It's taking us back to our 209 days. The mechanics version of this class, and we talked about those items. Those right there, the reality of all this got us to here. And we got omega's this, we got K is that. That's about it. Yeah, that's about it. Let me erase this. It's already something I've said. If we don't, it turns out we're not going to need it for this particular problem. We may need it down the road. Plug in the values. Now, they gave you, let's make sure we're all on the same page here. They told you a bunch of stuff. We could write it down. It's going to be a little bit of a mess, but we can do it. Let's deal with it. They already told me that E max was 0.05. 0.05 volts per meter. That's E max. Sine of a real long song and dance, but let's get it. It's going to be, we said K was 1.13 times 10 to the 7th X, and omega is 3.4 times 10 to the 15. T. I think it gets written a lot of ways here, but let's, you know, we got this, we got that, and that's K. That's K vector, the whole thing here. So at the end of that, all that, got the right units. That's K vector. We said the E field this time. They wrote it a little differently when they showed us in the notes, but it doesn't really matter. As long as they're oscillating perpendicular to each other, you can orient them anywhere you want. That's not going to be an issue. So you're going to take 0.05, which is E, divided by C, and get what seems to be a really small number. No, you get what really is a small number, but again, the units are different. So that doesn't judge the strength of the field you get. That doesn't, as far as like the power that is transported, they both transport the same amount of power. They both have the same energy density. And then we do this. You've got 1.13 times 10 to the 7th x minus 3.4 times 10 to the 15th t. Now that would be J. Sorry guys, I probably should have erased a few things. It's pretty visible though, right? Should be okay, right? It's okay? Or
it's okay for now, yeah, but if you can avoid using that color, it'll be better for the future.
Okay, is it okay now?
It's okay for now, yeah, I can get it. But
okay, don't do it again, okay.
Just
maybe
color.
Maybe use it to circle.
Sure, yeah.
But not to write, right?
Right. The red color is a little difficult to see.
Okay.
We can see it. We can see it now. But
do you want me to rewrite it? Do you want me to rewrite this or no? Should be okay. All right.
Yeah.
Okay. 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 I mean the basic moves, guys. I don't know if this. Hopefully this makes a little bit of sense. This is basically where the whole thing is. You plug in all the appropriate numbers. You plug in all the appropriate numbers and evaluate for this and evaluate for that, you're set. That's all I did here. It's not as visible, so I'm going to watch out in the future on that. But not as visible. That's all. This is just that. This is easier to look at. Just plug in the appropriate values of K and omega and Emax and C. And you're done. You're done. And we already said what K was, and we already said what omega was. Okay. So we got the K right here. That's the big thing. And like I said, the notes are maybe, in this regard, the notes are better, maybe a little bit better than my writing, at least in that one spot. Okay. That was 32. Let's look at 41. 41. Find the intensity of the electromagnetic wave described in each case. An electromagnetic wave with a wavelength of 710 nanometers and a peak electric field magnitude of 2.5 volts per meters, and B, an angular frequency of 7.5 times 10 to the 8th radians per second and peak magnetic field of 10 to the negative 10 Tesla. So, find the intensity of the electromagnetic wave described in each case. An electromagnetic wave with a wavelength of this. Now, this is rather interesting. Let me erase a good number of things right now, and we'll kind of take it from there. I think I'm going to erase everything I wrote on this. Let's just get right to 41 and start it from scratch, if that's okay. All right, the way the question gets asked is a little bit on the confusing side. So let's look at it. Let's see what we can say regarding this thing. So they're given two different scenarios, and it almost doesn't look like two different scenarios, but so let me say.
I am.
Where? Okay, let's go. Thank you very much, everybody. Let's keep going. 41. Find the intensity of the electromagnetic wave described in each case. For number 41, chapter 34. an electromagnetic wave with a wavelength of 710 nanometers and a peak electric field magnitude of 2.5 volts per meter, and B, an angular frequency of 7.5 times 10 to the 18 radians per second, and a peak magnetic field of 10 to the negative 10 teslas. Okay, it's a little bit confusing the way they do it. I think the way we're going to have to find this out is to look at the stuff that is actually available to us regarding that. They tell us that the intensity, let's have a look here. We talked about the intensity. There are a number of things we can say here. Mathematically, the energy transferred by an electromagnetic wave per unit time is given by this. The intensity of an electromagnetic wave is the time average of S. So there's a lot being said here, I guess you could say. That per unit of time is this, so let me actually write this thing out as best I can. They're telling us, just write it out. The three equal signs right there . 1 over mu 0 E vector cross B vector, and that is going to be, well, let's figure out what that is. Let's find out what E vector cross B vector is, and we'll go 1 over mu 0. Should be pretty easy stuff. When you do this, let's just write out some mathematics here and see what we can say. J, and you're going to cross what does that equal? Well, they're perpendicular to each other, so it's going to be E times B times the sine. That is the sine of the angle between them. The sine of the angle between them, they are perpetually perpendicular to each other. So that's just going to be E max, B max, E max, B max, and then sine squared of the quantity kx minus omega t. The other sign I'm talking about is the sine of the angle between the two oscillating quantities. The oscillating quantities, all the vectors that are present, the oscillating quantities, they are perpendicular to each other. Remember, the propagation is taking place like this, let's say, and these two guys are there's oscillation straight up and down this way, and there's oscillation sideways, and they're perpendicular to each other. Don't worry about I hat, J hat, and K hat. Whichever one of those you're using, I hat, J hat, or K hat, as the direction of propagation, the other two directions are going to have an E field and a B field perpendicular to one another. Or even if they're not in those particular planes, they are always in planes that are perpendicular to one another. So this is it. So this holds, and we do the whole song and dance. Now if you go J vector cross K vector, J vector, K vector, J vector cross K vector, roll right hand, bam, your thumb goes that way, that's I hat. That's I hat. That's I hat. So it's as simple as that. Now if you want to make it for the pointing vector, the intensity, the time intensity, is the average of the pointing vector. And so, I mean, there's a lot to say here regarding that. So we can say here that there's a lot going on here. So, well, what do we know? Well, we already did this. We already did this at some earlier time. The average of the square of the sine function is a half. The average of this guy, as complicated looking as it is, it's still a sine function. The average of the sine function squared rather, still the sine function squared. The average of the sine function squared is a half, and we've already discussed that. So, what does this mean? Well, I mean, we said this is going to get us here. If this is the Poynting vectors in terms of magnitude, it's going to be 1/2 E max, B max. It's in the y direction, you know, it's in the I direction, we know that. And let's see where we're going to go. So we wrote this. See exactly where we want to go with this. We are always remembering at least, that E is going to be CB. The units are different. The amount of energy transported by both parts, the B field and the E field. The B field and the E field transport the same amount of energy. Very important to know. On average, you're transporting the same amount of energy. This is just different units, and that's why it looks different like that. So don't ever be thrown off on that. We can look at it. Let's just make sure we got it straight. That's E, that's this. It looks pretty good. Let's see exactly what we want to say regarding this. So I think what you want to say is the half is the half. The mu zero is that. For some reason here, guys, let me see, make sure I had the right stuff on here when we did it. Right. We should maybe not the biggest problem in the world. You got this, but you remember this is what that's all about. So the magnitude of this guy. So you could play it a whole bunch of ways. I'm debating with myself where to go here. If you're just finding this, in the end, you're going to find. To find S vector, it's going to be 1/mu0 times this quantity. So get all this, get the answer, get down to here. That implies that's the average magnitude of the S vector. So actually it isn't. That implies that try to think here where exactly how I want to write it. If you want to write the S vector, you guys, you're going to write it a whole bunch of ways. We got this at the very end. So what you have to do is, this implies 1/1/2, which is what this is, times 1/mu0. When you put the 1/mu0 there, then you've gotten the magnitude of the Poynting vector. We didn't, see, this didn't have the Poynting vector initially. The Poynting vector was all this. I negated to put, I just found this one out, and at the end I put 1/mu0. So find all this, that's that. Now multiply it by 1/mu0, and this is the magnitude of the Poynting vector. And see what else we could say here about this. Now we say that the B vector, B, the magnitude of it is E/C. So for B max, it's E max over C. So it becomes, all of this becomes 1/2mu0 C E max squared. And that's the average. And that's the average intensity of the whole, in the whole process. The average S vector, the magnitude of it, the average of that. The average of the S vector is coming out to here. And you can, that means a lot of stuff. You can leave it like this, or you can say, well, what's E? E is going to be CB. Why don't you put the C, why don't you put CB in place of E? That becomes C squared B squared. C goes into there. It's 1/2 C over mu 0 . So there's a lot of looks that you can have for it. You can have this, and you can have this based on that. So if you put for A, you're saying how would you do this given that they gave you the E field? Now they gave you the E field, so you got to solve in relation to the E field. 2 mu 0 C. They told you that was 2.5. Square it, you get 6.25. 2 is 2. Mu 0 is 4 pi times 10 to the negative 7. C is 3 times 10 to the 8. If you actually knock that out, we're getting, I'm going to run out of room is what I'm going to do. Let me go over here. I'm sorry, guys. Let me stay with that. Or come with me, rather. I'm sorry. Remember what we wrote there. We got essentially, so I guess that's why they were given the two scenarios there and saying, okay, well, let's say I only gave you the magnitude of the E field. Do you know enough to do it? And then the other stuff is 2 4 pi times 10 to the negative 7. That's a lot here. I mean, there's a lot there. When you do it, equals I. There it is. I guess that's why they asked the question like that. The big thing I keep debating with myself on this thing. The magnitude of the, here's the S vector. The S vector is given by this quantity. The S vector is given by that quantity. And we are told that if you find the magnitude of the S vector on average, the average magnitude of the S vector is the intensity. Great. We know that E equals CB. We know, likewise, because of this, that B equals E over C. Which came first, the chicken or the egg? We know this relationship holds. E equals CB, which means B equals E over C. We know that the intensity is the average of the average magnitude of the pointing vector is the intensity. We know E equals CB, we know B equals E over C. From there, a lot happens. So if you since what the heck, we're taping, we're there, let's change the way we're doing it. If you want to do that, stay with it and make this guy 1 over mu 0 times that, which is what? Well, it's 1 over mu 0 times that. At the end of that whole song and dance, it's 1 over mu 0 times all this, which is 1 over mu 0 times 1 over 2 is this, which is that. Not a big deal. Either way, as long as you remember to do it. As long as you remember to take E vector cross B vector and multiply it by 1 over mu 0, then you got the magnitude of S vector. Okay, so that is that answer. Now they're saying the other way, what if they flip it around on you? They just, see here, why did I do B like this? ladies and gentlemen, I can use this. So this is a big thing. I mean, we can use this, or I can use this, depending on what they told me. One of them, they told me the E field, so I'll use this one. The other one, they're telling me the B field, so I'll use this one. I've established the equations already, so it doesn't matter how so either one's going to work. For A, they gave us the E field. For B, they didn't give us the E field, they gave us the B field. All right, those things over here, underlined in blue, are going to work. One or the other is going to, depending what they give you. They give you the E field, use this. They give you the B field, use that. It's that simple. So if that's the case, for B, they're just asking for the same game, same kind of argument, I guess you could say, for B. Okay, looks just like what we did. It's got to be MKS system of units. This is another set of parameters. It's not the same wave. If it was the same wave, it'd have the same answer. It doesn't matter. This is a big thing, guys. If I was solving for B, if I was solving using B or solving using E, if it's the same wave, whether I use E or B, I'm going to get the same answer. Here it's a different wave, and they just gave me, for A, they gave me the E field, but not the B field. For B, they gave me the B field and not the E field. So what do you got to use? Use the E field for A to solve, and for B, you got to use the B field. So, and there it is. There it is. That takes us through, or at least a little bit through. I mean, it says something about, there's a lot of stuff here, guys. Obviously, there's a lot of stuff here. But that takes us a little bit through chapter 34. Chapter 35 is problems 7 and 8.